All right, we're going to look at the next section of the book. This is section 3.2, and we're going to look at a new class of functions called exponential functions. Okay. And the idea is we're going to try to flip around the terms that we're working with. So what have we done up till now? We've looked at things that look like constants. We've looked at things that look like x and plus constants, and we get linear relationships. We've looked at things where we take x squared plus something times x plus something times 1. We get parabolas, and we keep doing this and talk about polynomials. In fact, we can talk about square roots and cube roots and such. And we can think of these as taking x and raising to a number. Now what we're going to do is we're going to reverse this. We're going to ask, what happens if we turn this around? What if we ask what happens when we take a number and raise it to the x? And what do these functions look like? And what we're going to get is a class of functions called the exponential functions. Okay. So I'm going to focus on this one first and see what happens, see what we get. Okay. So see if we can graph that thing. We're going to do our standard thing. We're going to build a table. Plug in different values for x, see what happens. So let's see, if I plug in x equals minus 3, I'm going to get 1 over 3 cubed, it's 1 over 27. I plug in x equals minus 2, I'll get 3 to the minus 2, or 1 over 3 squared. X equals minus 1, I get 1 over x. X equals 0, 3 to the 0, we're going to define that to be 1. Okay, it's just going to make everything consistent. 3 to the 1 is just 3. X is 2, 3 squared is 9. 3 raised to the 3 is 3 times 3 times 3 is 27. If I were to plot this thing, let's see, so I've got minus 1, minus 2, minus 3, 1, 2, 3. So this is going to be really close to 0. This is still close to 0, a little higher, and this is going to go up to 1. This is going to go up to 3, this is 9. This is like way up there. Okay, so if I graph this thing, what's going on? Oops, and I kind of missed it. I get something like that. Okay, so this is 3 to the x. So now what's happening? This thing, as I come out to here, is getting closer and closer and closer to 0. As I go that way, this thing grows very fast. Okay. In general, if we look at this thing, okay, if we compare this to other functions, in terms of polynomials, that function I just did is going to grow faster than any polynomial. Okay, so my 3 to the x, if that looks like that, y equals x is going to look like that. Y equals x squared is going to look like that. Y equals x cubed is going to look like that. And I can keep going, and in the short run, y equals x to the 4th or y equals x to the 5th may get above this, but eventually this is always going to win. So these exponentials will always be bigger than any polynomial. And notice I made a mistake here. There's another thing that's happening here. Notice the y cubed, I got excited, doesn't come back up. It actually comes down like that. Okay? So notice another difference here is these exponentials out here. This particular exponential is going to die off and get close to 0, and then it goes off to here, whereas these polynomials have this other kind of behavior for large values of x. In particular, what's going to happen? If I were to compare say y equals 2 to the x to y equals 3 to the x. Out here, it's going to get closer to 0 faster. But out there, it's going to grow much faster. Okay. Likewise, if I have y equals 4 to the x, it's going to get closer to 0 out here. It's going to go through the same point here and get much faster. If I flip things, if I turn this around, and now if I graph y equals 1/2 to the x, I'll get something like that. Okay. If I graph 1/3 to the x, I'll see kind of the corollary here of what we just saw. It's going to grow faster for negative x, but get closer to 0 for positive x. And likewise, if I look at 1/4 to the x, it's going to do something like this. So in general, what's happening? I look at y equals a to the x, I compare it to b to the x. If that's a to the x, and now if I assume a is greater than 1, we're going to see something like this. And now if I assume b is bigger than a, we're going to see it growing faster here, but getting closer to 0 out here. Now if I turn this around and assume that both a and b are between 0 and 1, what happens? Okay, so now both a and b, let me do this. A is between 0 and 1, and I'm going to assume that b is bigger than a, but is still also less than 1. So what's going to happen? My a to the x is going to look like that. Because b is bigger than a, let's see, so if I give it a negative number, it's going to, let's see, not grow quite as fast. So this thing here, since it's closer than a, and I'm raising it to positive powers, it has to get closer to 0 faster. Oops. Use this. So I will get something like this. Right? So now this is a case where a is closer to 0 than b, and for positive values of x, b to the x is going to be bigger, but b to the x is going to be smaller than a to the x for negative values of x. Okay. Now, why are we worried about things of this form? We know how to deal with compositions and shifting and all that kind of stuff. So if I know how to deal with y equals a to the x, I can deal with a new function, we'll call it Beth. And what is Beth? Beth is 1/4 times 3 to the x minus 6. So I know how to talk about 3 to the x. So let's see, so 3 to the x looks like that. Now if I multiply by that by 1/4, I know I'm going to scale it vertically, and then if I take that result and shift it down by 6, then I know what that new function is going to look like. So understanding how to use that, or what that means, and how to interpret that, will go a long way to working with general exponential functions using the same techniques that we saw in the previous sections. Okay? All right, so where is this used? Why do we care about this? Does these things even come up? look at a particular example. These come up in many different situations in science and engineering, but they also come up in finance. And that's what I'm going to look at. So your banker uses this. Your banker plays a game. And here's the game your banker plays. I'm going to take $100. I'm going to put it in an account, and I'm just going to walk away from it and see what happens. Okay? Nothing happens the first month. The first month, there's just $100 in there. Okay? My banker is going to tells me he's going to compound the interest rate monthly at some given rate. So what does that mean? In month 2, or after the end of the first month, the banker is going to take that and multiply by some rate R and add to what I had. I'm just going to sit there for a month and not do anything. What happens after that? At the end of that second month and going through the third month, what does the banker do? The banker takes the previous balance, lets it ride, but the interest he gives me is based on the previous balance. So I get that. Oh, that's a mess. Let me see if I can clear that up. Now notice, I've got 100 plus R times 100 here. I've got the same term right there. So I can take that whole term, I can just factor that whole thing out, right? I just think of that as some number. So if I take that number, okay, I can factor that out. I'm going to get 1 plus R. Oh, look. There's 100 that's in there, right? I can take that out. If I do that, if I take 100 from there, I get 1. Take 100 from there, I get R. What do I have? I've got 100 times 1 plus R quantity squared. All right, so what happens now? At the end of the third month, the banker takes my previous balance, lets it sit there. Then, what's he going to do? He's going to take that amount and give me some interest on that. We'll call it R. So whatever was there, he just gives me R times that. Okay, what do I have? Notice, that thing and that thing is the same thing. So I can factor that out. Let's see, so if I take that out, that's just 1 times that, but this is R times that, so what do I get? I get basically this thing cubed. And when you do this the next month, you'll get this thing to the 4th, the next month that thing to the 5th, it just keeps going on and on and on. Okay. All right. Now, unfortunately, your banker plays a different kind of game here. Okay. I was played it a little fast and loose here with what this R means. Your banker doesn't tell you what that R is. Instead, your banker gives you what's called an annual interest rate. We'll call that capital R. And the R that he puts there, if this is monthly, then it's going to be the annual rate divided by the number of periods, which in this case is 12 months in a given year. Okay? So what do we have? After M months, my balance It's going to be the initial thing times 1 plus this r, which I'm going to call r over 12. And I'm going to raise that to the m for the number of months that has been sitting there. Okay. Problem is I don't like that. Okay. I want to talk about this in terms of years, because that's an annual interest rate. I want to keep all my units the same. So the question is how do I write this as in terms of the number of years that's been in there in order to keep all my units consistent? Well, what do I have? My number of months equals m. So how do I get the number of years? Well, I know that there are 12 months per year. So let's see, that means then that, let's call that t. 12 times t will give me the number of months. So for example, if t equals a half, I'll have 6 months. So that means that my t is m over 12. Oops, sorry, that's wrong. So I just have, basically just have that, okay? So that means my balance, that is going to be 100 times 1 is r over 12. The number of months is 12 times the number of years. Okay? So what happens in general? In general, what can happen? Before I go on, I just want to reiterate what this means. Is this thing is a exponential function. So I was talking about a to the x before. That 1 plus r over 12 is a constant. That's my a. And there's my x. And you can think about this as scaling this thing horizontally. Okay? So what do I have? In general, your banker gives you an annual interest rate, but that's a little bit of a lie. That's not the interest rate that actually gets charged to you. Now look at the detail. So that interest rate is compounded so many periods per year. So if this is 12 periods per year, n would be 12. So this is monthly if n equals 12. If it's quarterly, that means it's every 3 months. This would be 4. Right? So quarterly means this gets compounded 4 times per year. We have the number of years that we're going to let this thing sit. And we have some initial balance. So the current balance then is going to be the initial balance. I'm going to multiply by 1 plus, that's the effective interest rate that's charged each interest period. And that's a definition. That's just how the banker defines it. Times the number of time periods it gets compounded, which is going to be n times t. And now we have the balance for finding, the formula for finding your balance when you compounded interest, and you have the number of periods per year, number of years, and something called the annual interest rate. This is the formula your banker is going to use to figure out how much money is in your account.